Okay, so we're on to lesson 2, which is Hooke's Law. We're just going to develop an understanding of Hooke's Law by firstly identifying what it is, testing it experimentally, which you can do in the lab. If you can't, I've got some results on this PowerPoint. Analyse the data to provide a simple conclusion, and if you're really doing well, you could think about the ideas of proportionality and using a graph to give weight to your argument. So if you actually bring the graph into explaining what you're doing. Common problems with this whole setup are people are not sure between what length 1 and length 2 is, and it's thinking that there's the actual length of extension and then there's the original length of the spring, so just try not to get confused. So making a prediction then, so the first thing you could do is think about what would it look like if I added weights to a spring. It'll get longer, we know that. It could be a straight line, and then it sort of goes a bit funny. Could be a hump, a bit weird, but there we go. Could be where it extends and then seems to change on its extension. So there's this one and this one that could be a bit unusual. That one's maybe a little bit far out. That might be traditionally what you'd assume. So your experiment, you set up the equipment as shown. You load up your spring. It gets to what we call the elastic limit. Then if you go too far, when you unload, you permanently extend it, so watch out for that. The formula that we use all the way up to A-level physics is F equals Kx. So F is the force, K is the spring constant in newtons per meter, and X is the extension in meters. Now if you plot the graph the right way around, so if you have F on the y-axis and X on the x-axis, K would be your gradient, and that would be the spring constant or stiffness of your spring. So the nice little worksheet to fill in, you've got some results, loading and unloading, I've got a mean. The PowerPoint then explains about the idea of proportional, so what we're talking about is a straight line, like a linear relationship, and then clearly it curves as it starts to deform, what we call plastically permanently deformed. Okay, so if it was a proportional relationship, it would stay straight. If it's not proportional, you'd end up with this sort of curved graph. Like we said, it starts to plastically deform. You might see that on your results, you might not. So you can think about your results. I've got a set of results plotted already. I've got some helper statements there on the PowerPoint for your conclusion. It's also thinking about how the bonding is within materials. So we've got a typical metal spring, which should be a lattice of ions here, so this could be copper, aluminium, or whichever metal. Electrons wand their way through. Now metals tend to behave in a certain way, eventually they slip over each other, whereas an elastic band, it's all kind of like higgledy-piggledy. So all of the little strips of rubber that are in an elastic band, as you pull, they all kind of unravel. So elastic bands behave a lot differently. You've got a reverse view for your axes there, little marking criteria. We've got some structured questions and you've got some answers. So you can work through that at home, and you've got a nice little plenary to think about how it all works. Now the last part is the potential energy stored in your spring. So how much energy, as I've pulled it down, as it got in there, is the potential energy is a half times the force times the extension. So you can find for a point on the graph, technically it's like the area under the graph. So there you go, that is your lesson 2 for forces and pressure.